So that was, we looked at double angles. T results you can kind of think of as half angles. And so what we basically are doing is we're turning trig into polynomials. So we'll let t represent tan of a half theta. Now, if that's true, then I know tan theta, because now I'm using the double angle result, would be 2 tan theta on 2 on 1 minus tan squared theta on 2. But I'm letting tan theta on 2 represent t. So it ends up becoming a piece of an algebra there, an algebraic fraction. 2t on 1 minus t squared. Now, if I draw up a triangle, I can get a result for sine and cos as well. So if tan is 2t on 1 minus t squared, opposite over adjacent, bit of Pythagoras, we can work out the hypotenuse eventually. There's a perfect square. So it'd be t squared plus 1 would be the hypotenuse, or 1 plus t squared, either way. So I can read off that, and so we now know that if t is tan theta on 2, okay, tan theta, 2t on 1 minus t squared. Sine theta, 2t on 1 plus t squared. And cos theta will be 1 minus t squared on 1 plus t squared. So that's what we call the t results. How we came up with that name, I'll never know. But remember, again, we're talking about doubles and halves. It doesn't have to be tan theta represents 2t on 1. If I made t equal tan theta instead of tan theta on 2, then now tan 2 theta would be 2t on 1 minus t squared. If I made t equal to tan 2 theta, then it would be tan 4 theta would be 2t on 1 minus t squared. So we're not restricted for using the t results just for sine of theta, cos of theta, and so on. It can be whatever. It's just what we let t represent. T has to be tan of half of whatever the angle we're playing with. We're going to show that 1 minus cos x on sine x is actually the same as t, where t is going to represent tan x on 2. So we'll sub in our t results. So x is double x on 2, t results for sine and cos. We get 1 minus t. The nice thing about this one is the denominator, you'll notice, is the same. So all we're going to do, multiply everything by 1 plus t squared. So the 1 becomes 1 plus t squared. And on the top, what are we left with? 1 minus 1, we just got 2t squared on 2t, which is t. And that's what we wanted to prove, or show. Again, they're telling us, use the idea of a t equals tan theta on 2 to simplify this one. This is like the problem I just had with the other one. Before it was a problem, because I had 1 plus t squared on the bottom instead of 1 minus t squared. But now it's not a problem, because if I look at that, I can say, hang on a sec, that's a t result. 2t on 1 plus t squared. I just got to remember which one it represented. 2t on 1 plus t squared was the sine, yeah. So basically, if I let t equal tan 75, then theta on 2 is 75. If I'm using t equals tan theta on 2. So I know theta is 150. So my 2t on 1 plus t squared is sine theta. I'm finding sine of 150. 150, second quadrant. Acute angle is 30. So that's a half. Now, we've got to prove this one. 1 plus sine theta minus cos theta, 1 plus sine theta plus cos theta, all ends up being tan theta on 2. When I see double angle, I'm either going to use double angle results or t results. It actually doesn't really matter, but it probably makes sense to use t results because we're going to end up showing tan theta on 2. So I'll do that. I'll let t equal tan theta on 2. Substituting my t results. Now, whilst it looks awful, the denominator, again, is all 1 plus t squared and everything. So if we just multiply everything by 1 plus t squared, tidy up the numerator and the denominator. So I now have 2t squared plus 2t on 2 plus 2t. Algebraic fractions. See, we've changed a trig question into an algebraic fraction question. And algebraic fractions, we always factorise first. So let's factorise top and bottom, and we can see the cancelling now. So 2's will cancel, t plus 1's will cancel. I'm left with t. That's not the final answer for this question. Remember, they have asked you to show that it's tan theta on 2. At this stage, we've showed it's equal to t. Okay, but we did define t somewhere. There it is. So now I can substitute in and say, yes, but that is tan theta on 2. Okay, let's have a look at nature C1. Again, they've told us to use t equals tan theta on 2. It does say or otherwise, so I mean, if you do see another way of doing it, by all means. But usually, when they say it like this, they're saying, here's a really huge hint. This is probably going to be the easiest way of doing it. Show that cosec plus cot of theta is cot theta on 2. All right, cosec. Well, cosec reciprocal of sine. So we want the t result for sine upside down. And cot is the reciprocal of tan. So we want the tan one upside down. That's nice because the denominators both turn out to be 2t there. So we can add those together. 2 on 2t, 1 over t. But that's got to be the cot of theta on 2. Because we said t was tan theta on 2. So we've got the reciprocal of t, reciprocal of tan is the cot of theta on 2. Alrighty, there we go.